Now let us finish our discussion of section 1.1. Did anybody try to solve these problems at home?
I did like A, B, C, and D.
Maybe you can tell us, how did you solve problem A? What was the rationale? What was your approach?
I looked for like different elements of the pattern. Like I first saw that it was like interchanging signs. So I knew that you had to have -1 to the k plus 1 or -1.
So you started with a sign. Tell me, in this problem, you started with -1 to which power?
I use +1 because -1 to the 1 is -1.
Give me a second. When you create your general formula, you raise -1 to which power in order to generate all these numbers?
K plus 1. Because I started with k equals 0.
Give me a second. You can. Here a 1.
Oh, I see.
So to which power we raise -1?
You'd have to have k, not
K
plus 1.
absolutely. Yeah. So here, in order to come up with alternating signs starting from negative, we raise -1 not to the power k plus 1, but to the power k. Okay, next, how do we come up with tops and bottoms?
I just looked at how the numbers were changing from each one, and I saw that the first one was just increasing by 1. So I just had it as k plus 2. So it was just 3, 4, 5, 6, 7. And then I did 2k plus I think it was 6, I think. Yeah.
So give me just 1 second. Let us talk about tops. The formula is k plus 2. Is this correct?
Yes.
Sure. So since the top for A1 is 3, the top for A2 is 4, and so on, the general formula for the top is k plus 2. How about the bottom?
Be 2k plus 4. 2k plus
Why
6,
did you...
I think.
Give me a second. So let me start with 2k. Why 2k, not 3k, not k, not 7k? Why?
Because it was incrementing by 2 each time.
Because the difference between any two consecutive numbers is 2. How do we call this sequence? 8, 10, 12, 14, and so on.
Arithmetic.
Arithmetic sequence. We discussed it over here. The general formula is dn plus a0, where a0 is the initial term, d is the difference between any two consecutive terms. 11 minus 5, 6. 17 minus 11, 6. 23 minus 17, 6. It's exactly what we have here. 10 minus 8, 2. 12 minus 10, 2. 14 minus 12, 2. Therefore, the general formula is 2k. But then 2k plus what?
The way I did it is I just plugged in the index, and then I just saw how much it was offset by, and I saw that it was the same for each one. So I did plus 6.
Absolutely. Since the initial value of k is 1, 8 should be equal to 2 times 1 plus x. And therefore, x is equal to 6. So the general formula for the bottoms is 2k plus 6. It's exactly what we have here, with an an is equal to -1 to n's power n plus 2 over 2n plus 6. And if we factor out 2, we'll get n plus 3. Similarly, sequence number 2, the only difference, instead of -1 to n's power, we have -1 to the power n plus 1. Okay, now B, how did you come up with a general formula for B?
I looked at the differences between all the numbers and saw that it was increasing every time. So
Okay.
it was like, you would have to like not just use an arithmetic sequence, but use geometric as well.
So you considered all differences. 2 minus 1, 1, 6 minus 2, 4. This immediately tells us that this sequence is not an arithmetic sequence. Let us see if this is a geometric sequence. 2 divided by 1, 2, 6 divided by 2, 3. We immediately see that this is not a geometric sequence either. So what do we do next?
Think about like how like with Fibonacci, how it like relates to the last two numbers, and maybe that.
Okay, so you tried Fibonacci. Fibonacci will be discussed later, but I can tell you, this is not a Fibonacci sequence. Fibonacci sequence, we create next term adding up two previous terms. This is not the case. 6 is not 1 plus 2. What do we do?
This is just factorials.
Okay. These numbers are values of n factorial. Why is that? And what is n factorial?
Oh, sorry, multiplying the consecutive numbers up to n.
Yes. N factorial is the product of all numbers from 1 to n. Of course, if n is a positive integer. For example, note that 6 is 1 times 2 times 3. So 6 is 3 factorial. 24 is 6 times 4. Therefore, 24 is 1 times 2 times 3 times 4. 120 is 24 times 5. Therefore, 120 is 1 times 2 times 3 times 4 times 5. Going back to these two numbers, 2 is 1 times 2, it's 2 factorial. And finally, 1 is 1 factorial. Guys, any questions about B?
Couldn't you also say it was like n times a n minus 1, like n times the previous term?
Very good point. Observe that 2 is 1 times 2, 6 is 2 times 3, 24 is 6 times 4, and so on. In order to jump from 1 to 2, we multiply by 2. In order to jump from 2 to 6, we multiply by 3. In order to jump from 6 to 24, we multiply by 4, and so on. So the formula is an is equal to an minus 1 times n. For example, a2 is a1 times 2. a3 is a2 times 3. a4 is a3 times 4. a5 is a4 times 5. This formula is absolutely correct. However, please take a look at this. We want to find explicit formulas. an is equal to an minus 1 times n is not an explicit formula. This is a so-called recursion. We find next term using previous term. Here we want to find explicit formulas. An explicit formula for this sequence is an is equal to n factorial. Guys, any questions here?
I have a question. You said that this one is not geometric, so is it just neither arithmetic nor geometric?
Are you talking about B?
Yes.
This sequence is not an arithmetic sequence. This sequence is not a geometric sequence. Here's why. In arithmetic sequence, the difference between any two consecutive terms is a fixed number. It's obviously not the case. In geometric sequence, the quotient of any two consecutive numbers is a fixed number. It's not the case. 6 divided by 2 is 3. 24 divided by 6 is 4. Was that your question?
Yes, so we just wouldn't classify it as anything.
Yes, so this is not an arithmetic sequence. This is not a geometric sequence. This is something else. And the formula is an is equal to n factorial. Okay, what do we do with C?
I did, Professor.
Okay, what was your approach?
I kind of guessed, to be honest.
Okay, you guessed, fine, that's fine. So, but once again, even when we guess, we have some rationale. Which rationale? How did you guess?
Well, I first subtracted, found the difference between each number.
Okay, you started with the following. Maybe it's an arithmetic sequence. It did not work, right?
Right.
Because 12 minus 4 is 8. 28 minus 12 is 16. So this is not an arithmetic sequence. What do we do next?
Check for geometric.
Check for geometric. It's not a geometric sequence either. What do we do next?
I've seen this pattern in common difference before, so I kind of knew it was 2 to the power of something.
All right. So you basically observed that these numbers increase at a very fast rate. Is this true?
Yes.
And they don't look like factorial, right?
Right.
So basically, your rationale works. All right. It's not arithmetic sequence. It's not geometric sequence. It does not look like we have any sort of factorial, plus minus some number. So maybe this is an exponential function, correct?
Right.
Was that your rationale?
Yes.
All right. So, and what was your guess?
2 to the n plus 2 minus 4.
2 to n plus 2 minus 4. Basically, your idea was 12 is 16 minus 4. 28 is 32, again, minus 4. And 60 is 64, again, minus 4. And 124 is 128 minus 4. So these numbers are 2 to some power minus 4. Was that your approach?
Yes.
And the explicit formula is 2 to n plus 2 minus 4, which can be rewritten as 4 times 2 to nth power minus 1. Folks, any questions here?
Professor, is it possible that this is a combination of an arithmetic and a geometric sequence?
Basically, you are absolutely right. Please take a look at this. If we consider 2 to n plus 2 alone, this is a geometric sequence. If we consider negative 4 by itself, This is an arithmetic sequence. -4, -4, -4, and so on. And now we add geometric sequence and arithmetic sequence term by term. Was that your idea?
Yes, that was my idea. I'm just wondering if there's a way to convert from the 2ak minus 1 plus 4 into the equation that we have now, like to make it in the explicit form.
Okay, what you are saying is the following. Next term is previous term times 2 plus 4. So 28 is 12 times 2 plus 4. 60 is 28 times 2 plus 4, and so on. So we have the following recursion. AK is 2 times AK minus 1 plus 4. Is it possible to come up with an explicit formula? Yes, absolutely. There are methods that allow us to convert an implicit formula into an explicit formula. However, we do not discuss these methods in this course. The only exception from rules is Fibonacci sequence.
Okay, thank you.
All right, what do we do with D? Who tried D at home?
I did, Professor.
Okay, so what was your approach?
So my approach was noticing that, like, first ignoring the root 3 because that is constant in every single term. The fact that there is a root 3, so that can just be added on top of whatever the actual sequence on the inside is. From one term to the next, we're always adding 4. So 7 to 11, that's 4. 11 to 15 is 4. 15 to 19 is 4, etc.
Yes.
The inside, so that means that the inside of this is an arithmetic sequence.
Absolutely.
So so the inside would be 4 times n plus, in order to get that first term, plus 3. So the entire thing would just be the third root of 4n plus 3.
Absolutely. It's exactly how we do it. Step 1, observe that inside each cubic root we have an arithmetic sequence, because 11 minus 7 is 4, 15 minus 11 is 4, and so on. So each number can be generated by the following formula: 4 times n plus something. How to find this number? So we solve the following equation: 4 times n plus x is equal to 7, and replace n by 1. So 4 times 1 plus x is equal to 7 means x is equal to 3. The formula is cubic root of 4n plus 3. All right, now E. Any ideas about E?
Yeah, I have one, Professor.
Okay.
So I started first by taking the difference between all of the numbers within the signs.
Yes.
And then you'll note that it's 5, 7, and then 9, and then continues on in odd numbers. So that means that the second common difference, or the second difference in between those numbers, is constant, which is 2 in this case.
Mm-hmm. Yes.
So that suggests that it's a square term.
Okay, so your approach is, let us find the difference. n minus 5, 5. 17 minus 10, 7. So this is not an arithmetic sequence.
Right.
But let us continue. 26 minus 17, 9. 37 minus 26, 11. So let us list all the differences. 5, 7, 9, 11. These are consecutive odd numbers.
Mm-hmm.
And now those people who play with numbers a lot, these people know that if we add together consecutive odd numbers starting from 1, we will get a perfect square. Guys, we will discuss this later in the course. Let me show you the exact reference. Give me just 1 second. So if we click on mathematical induction, here we start with this wonderful property. The sum of consecutive odd numbers starting from 1 is a perfect square. Going back to this problem, in order to generate each number, we add to 5 consecutive odd numbers starting from 5. 10 is 5 plus 5. 17 is 5 plus 5 plus 7. 26 is 5 plus 5 plus 7 plus 9, and so on. This gives us the following general idea. Maybe these numbers are close to perfect squares. Was that your idea?
Yes, Professor, it was.
And how did you come up with the formula? What did you do next?
Well, after I got the idea it was perfect squares, it's pretty simple to just subtract 1 and see that they are perfect squares, and then build on from there.
Yes, we subtract 1. Note that 5 minus 1 is 4, which is a perfect square. 10 minus 1 is 9, which is a perfect square. 17 minus 1 is 16, which is a perfect square, and so on. The general formula is sine of perfect square plus 1. But this is not n square, this is n plus 1 square. Because if n is equal to 1, we have 1 plus 1, 2 square, 4 plus 1, 5. If n is equal to 2, 2 plus 1, 3 square, 9 plus 1, 10, and so on. Guys, let me give you another approach to this problem. We see that this is not an arithmetic sequence. I'm talking about 5, 10, 17, and so on. We see that this is not a geometric sequence. We see that this is not a factorial. We see that this sequence is not growing as fast as an exponential sequence. If you compare E and C, this sequence is growing really fast. So you compare these numbers with power of 2. These numbers are growing fast, but not this fast. So you compare these numbers with, say, to begin with, perfect squares, and you see, okay, it works. In other words, on tests, if you include problem of this type, I will not give you something terribly complicated. You should think about arithmetic sequence, geometric sequence, exponential function, factorial, and then either n square or n cube, something like this. Here you compare with n square, works. How about f?
If you compare with n cubed, it also works.
Yes, here simply by guessing, scientific guessing. So let us compare with cubes. The formula is n cubed minus 5. This is a really hard exercise. Now, a last question. 0, 1, 0, 1, 0, 1 looks so simple, but how to come up with a formula? Anybody?
I found one, sir.
Okay, yes.
Okay, I've noticed that it's a very periodic kind of sequence where it just alternates between two forms.
Yes.
And when I think of periodic, I think of trigonometric sine and cosine.
So we compare 0, 1, 0, 1, 0, 1 with sine or cosine. Perfect. What do we do next?
Well, if we look at, like, we could use either sine or cosine because they can be defined in terms of each other. I chose cosine in my case, where if we look at, like, I just drew a unit circle just so I can vision it a little better. So if we have cosine of pi halves, we have our first term to be 0 if cosine of pi halves is 0. Cosine of pi is -1, and then cosine of 3 pi halves is 0. And then we get 1 if you keep multiplying it by it. But the problem is that we're getting alternating negative and positive in that case. So I took the absolute value of that, yielding cosine of k times pi halves, the absolute value of which.
Absolutely. So here we have an explicit formula with sine, absolute value of sine of n minus 1 times pi over 2. Similar formula works with cosine. So once again, let us discuss this formula. If n is equal to 1, we have sine of 0, which is 0. We start with 0. If n is equal to 2, we have sine of pi over 2, which is 1. If n is equal to 3, we have sine of pi, which is 0. Now, careful. If n is equal to 4, we have sine of 3 pi over 2, which is -1. And absolute value of -1 is 1. For cosine, it's even easier. Absolute value of cosine n pi over 2. Now, another possibility is this formula. So let us forget this sequence for a moment and let us consider the following sequence instead. -1, 1, -1, 1, and so on. It's easy to generate this sequence. We just raise -1 to nth power. But here we have 0, 1, 0, 1, and so on. What do we do? If we add 1, once again, forget the fraction for a moment. Take a look at the top only. If we add to -1 to nth power 1, we will get the following sequence. If n is equal to 1, it's 0. Same as here. If n is equal to 2, we get 1 plus 1, 2. But we need 1. We just divide by 2. A3 is 0 because -1 cube is -1 plus 1, 0. 0 divided by 2 is 0. If n is 4, we get again 1 plus 1, which is 2 divided by 2, 1, and so on. Folks, we are done with section 1.1. Any questions here?
Yeah, could you also have used a modulo function for G?
Yes, we can, but first of all, we do not know modular yet. This will be discussed later. Secondary, here I ask you to find explicit formulas, meaning I need algebraic expressions.
Okay.